Hello dear students. In our last lecture, we have discussed about the laws of chemical combination. These laws which you have seen were given by Antoine L. Lavoisier and Joseph L. Proust, and you have seen these laws were based on the experimental observation of the experiments performed by Lavoisier and Proust, right? So, although these laws were very well explaining the observations of the experiments of these two scientists, but in science, whenever we observe something, there must be a theoretical explanation, right? So, Lavoisier and Proust could not give any theoretical explanation for these laws, and such theoretical explanation was provided by John Dalton, and he gave the theory known as Dalton's atomic theory, right? So, that Dalton's atomic theory, it gives us some more information about the atom, and it gives a theoretical explanation for the chemical combination, laws of chemical combination, right? So, let's first of all look at the various postulates of Dalton's atomic theory. According to first postulate, all matter is made up of extremely small particles called atoms, right? So, the first postulate of Dalton's atomic theory tells that every matter which we see around us is made up of some very tiny particles, extremely tiny particles, and these particles are known as atoms, right? Another postulate of Dalton's atomic theory is that all atoms are indivisible and can neither be created nor be destroyed during a chemical reaction. Clear? So, during a chemical reaction, no new atom is formed and no new existing atom is removed, or you can say disappear. Only what happens, the arrangement of atoms, the mutual arrangement or mutual joining of atoms change, right? There is no new atoms are formed here. For example, if we take the reaction of you can take any reaction. For example, we take the reaction of methane with chlorine. The reaction which occurs in presence of sunlight, the product here is chloromethane and hydrogen chloride gas. And you see that each and every atom during the reaction is conserved. If there is one carbon, here also one carbon. If 4 hydrogen, there also 4 hydrogen. If 2 chlorine, there also 2 chlorine, right? Only their mode of arrangement is changing. Initially, one carbon atom was bonded with 4 hydrogen atoms and chlorine was separate. But here, after the reaction, one of the hydrogen of methane has been replaced by chlorine. So, you can see very well that there is no change in the nature of atom, only what is happening, their mode of arrangement is changing, right? So, that is the second postulate of Dalton's atomic theory, right? Another one here is atoms of same element are identical in all respect, right? So atoms of same elements are identical, means they are having same shape, same size, same mass, and so on. And opposite to that, we can say the another postulate is that atoms of different elements are different in all respects, right? So when the same atoms, the atoms of same element are identical, at the same time atoms of different elements are different with respect to their shape, size and masses and all, right? Another postulate says that in a molecule atoms combine in a simple whole number ratio, right? That means in a molecule atoms are never present in the form of their fractions. The another postulate that gives you a very clear-cut idea that atoms are the smallest constituent particles of atom, as they can never be present in the fraction, means they cannot be further broken down into smaller components. And the another postulate of Dalton's atomic theory are that in a molecule number and type of constituent atoms is always fixed, right? So this postulate says that in a given molecule the number and type of constituent atoms is always fixed. For example, if we say that it is a molecule of ammonia, so whenever we say molecule of ammonia, means it is always containing the two types of atoms, that is nitrogen and hydrogen, that too in the ratio 1:3, irrespective of the source of the ammonia gas, right? So these are the postulates of Dalton's atomic theory, and as I have already told you that these postulates, they provide a theoretical explanation for the laws of chemical combination. So let's look at those postulates that give you the explanation for that. For example, if you look the second postulate, that all atoms are indivisible and can neither be created nor be destroyed. So this statement or this postulate explains the law of conservation of mass, because according to the law that mass can neither be created nor be destroyed, and this is only possible when atoms are also neither created nor destroyed. So as atom is neither created nor destroyed, of course the mass is also neither created nor destroyed, right? Then look at the postulate, last postulate. In a given molecule, number and type of constituent atoms is always fixed. So this of course gives you the explanation for law of constant proportion or definite composition. Same was said in law of constant proportion, that according to the law, in a given compound the same type of elements combine, or the fixed type of elements combine in a definite ratio by mass, and same is explained by this postulate, right? So as I have already given you the example of say ammonia, that in ammonia molecule, when we talk about ammonia, it becomes very clear that ammonia is a molecule which is made up of two elements, nitrogen and hydrogen, where the number of atoms of two elements are always in the ratio 1:3, right? But despite all the advantages of Dalton's atomic theory, the theory suffered from some serious limitations also, because in further studies there were some observation, and these observations put a question mark to the postulates of Dalton's atomic theory. Like as it was said that atoms are indivisible. Are the atoms really indivisible? No. The further studies, they show that atoms are further broken down into smaller subatomic particles like electrons, protons and neutrons, about which we will be discussing later on. So, the discovery of electrons, protons and neutrons, it puts a question mark on the indivisibility of atom. So, now we can say after the discovery of these subatomic particles, atoms are no more indivisible, right? Similarly, it was said here that atoms of same elements are identical in all the respect, but again, there is a question mark after the discovery of isotopes. Later, we will be discussing about isotopes, and you will observe how discovery of isotopes, it puts a question mark on this postulate. Similarly, discovery of isobars, it gives another question mark about the different type of atoms of different elements, right? And look at the fifth postulate, according to which in a molecule, atoms combine in a simple whole number ratio. Here, you will observe that atoms combine in whole number ratio, but that whole number ratio is not always the simple ratio, right? That is whole number, of course, and whole number shows that atoms are indivisible. They can never be present in the form of fraction. Let's talk about the molecule like sugar having formula C12H22O11. In this molecule, atoms are present in whole number but not in simple ratio, right? So that is about the Dalton's atomic theory. Now another interesting aspect about which we want to discuss here is that what about the size of atom? So as we know, atoms are the smallest particle of a matter. Then how small are these smallest particles? So if we consider the size of atoms, we must say that these atoms are extremely small. They are small beyond our imagination. They are so small we can't even imagine. We can't even have an example or comparison which can tell you that how small are these atoms. They are small beyond our imagination. Like if I put a dot with the help of this chalk, I think perhaps this dot may not be visible to you, but this small dot of chalk, can you imagine how many particles of or how many atoms are there? Even this small dot is containing millions and millions of atoms. Or you can talk about, you can look at the sheets of your notebook or book pages, right? So look at the thickness of the page of your book and you will see that this much of thickness can be achieved if we stack millions of atoms over each other. I hope these two examples would be giving you an idea about the size of an atom, right? Now, you must be wondering, when these atoms are so small, What is the significance of these atoms? Why we are so much bothered about these atoms? Because the variety of matter which we observe around us, whatever you see, any kind of matter, all these matter is made up of these tiny particles of matter, and of course these tiny particles are atoms. So these atoms may combine in different ways to give you different form of matter. At present, around 118 type of atoms are known. With this much only 118 types of atoms, we observe a huge variety, because the same atoms they combine in different ways to give you different types of matter, or to give you different types of compounds. Like for example, if we take the example of elements like carbon, hydrogen and oxygen. These carbon, hydrogen and oxygen, they can combine in different ways to give you different compounds or different forms of matter. For example, first of all, take the case C6H12O6. That is what? You know very well, that is glucose. If they combine in the way C12H22O11 is sugar. If we talk about CH3COOH is acetic acid, or which is commonly used as vinegar. If we talk about C2H5OH, that is alcohol, which we use for a number of reasons. So here you have seen just a small example. I have just taken the small example. There are again number of compounds which are obtained by the definite type of combinations, different types of combination of these elements, carbon, hydrogen and oxygen. So the various ways of combining of these elements that give rise to variety of matter around us, and that's why it becomes very difficult, important or necessary to know about the atoms. If you want to have an idea, or if you want to get some knowledge about the matter, first of all you must know about the atoms, right? So now there is another thing, that is about the symbols of matter, or symbols of atoms. So if we look at the symbols of atoms, the first kind of symbols were given by Dalton, and Dalton has given the symbol of these atoms, and they were on the basis of some of the properties or appearance of the symbol of the element. And of course here the symbols given by Dalton were not only qualitative, they were quantitative also, because each symbol represents one atom. For example, according to Dalton, this is the symbol of element hydrogen. It is the symbol of element, that is oxygen. If we look at the symbol of phosphorus, it is the symbol of phosphorus, or that is the symbol of iron. So here are a few examples giving you an idea about the symbols as were given by Dalton. But later on, Berzalius provided the symbols on the basis of alphabets in the name of the element. For example, for carbon it is C, for oxygen it is O, for nitrogen it is N. Initially the names of the symbols were given on the basis of their properties, or their origin, or first where they were observed, like that. But nowadays The symbols of elements are decided by an organization known as IUPAC, which stands for International Union of Pure and Applied Chemistry. According to IUPAC, the symbol of an element is given on the basis of its name, maybe English name, maybe Latin name, maybe Greek name, and in that case, the first idea is to use the first letter of the element as its symbol. Like for example, as I told you, for carbon it is C, for boron it is B, for iodine it is I. And if the two numbers they share the common initial letter, then maybe their second, third or last alphabet is put here as the symbol. For example, carbon, chlorine, copper, cobalt, they all start with C. So for chlorine it is Cl, for copper it is Cu, for cobalt it is Co, and so on. Boron starts with B, having symbol B, and another element, bromine, is given the symbol Br. If we talk about iodine, starts with I, then another symbol, iridium, element iridium is having the symbol Ir. But one should be very careful while writing these symbols, that in these symbols, the first letter is always capital and the second one is always small. Look at these symbols, chlorine, copper, cobalt, bromine, iridium, right? So you can see very well that the first letter or first alphabet is capital, another one is small. Be very careful, because sometimes if you don't follow these rules, it makes another thing. Like if you put capital C, small o, then it stands for the symbol cobalt, right? And if we look write like this, capital C, capital O, it's no more cobalt. It is the compound known as carbon monoxide, right? So a small negligence can change the whole thing. And also many times their names have been obtained not from their English name but their Greek or Latin name. For example, if we talk about sodium, it is given the symbol Na on the basis of its name, natrium. If we talk about iron, it is given the symbol Fe on the basis of its name, ferrum. If we talk about copper, which is having symbol Cu, is on the basis of its name, cuprum, and so on, right? So that was an idea about the atoms and their properties. In our next class or lecture, we'll be discussing about the mass of an atom. How is the mass of an atom measured and expressed, and how these atoms exist? That all we'll be discussing in our next lecture. Goodbye till then. Have a nice time.